Welcome to the fifth of 7 videos covering quadratic theory at higher maths. This one is going to focus on a slightly more in-depth coverage of the discriminant. It has been mentioned in the recap video in number 1 of quadratic theory, but I'm going to go into a wee bit more detail here. Again, this is more prep work in preparation for using the discriminant in much deeper context within the higher course. I can't stress enough how important understanding the discriminant is for you to be able to understand lots of other concepts. So it becomes quite an important building block for your kind of future success within the maths course. So learning intention, I want you to be able to use the discriminant to determine the nature of the roots. This is generally a National 5 recap, but some of it is in that kind of blurred area where we're not sure whether it was considered a National 5 skill and when it becomes a higher skill. So I'm covering both, as in this could come up in its own right as a context question at higher, but it may or may not, depending on what the SQA say fit, as in what they would put down to National 5. And given the relatively young nature of the course, I can't for certain say which is which. So again, cover it now and be prepared to use it at higher. So, two of the most common uses for the discriminant are to identify the nature of the roots of a quadratic. Now, at higher, this will most likely be part of a bigger context. It won't just ask you to determine the roots. Determining the roots will tell you something. It will allow you to do something else. So you will determine the nature of the roots of a quadratic, but it will allow you possibly to do something else within all the other contexts in the course. And again, only as we go through the course will you start to see and be able to understand its full power. So at this stage, I can give you some examples, but I can't give you the full range because you haven't necessarily covered all the coursework to be able to do that. So as we go through the course, you will see more and more of the discriminant and will therefore do more and more practice. As we go through even just the quadratic theory videos 6 and 7, we will do a lot more with the discriminant in regards to that, and again in future topics. Second common use is to determine a missing value in a quadratic based on information about the roots. This is likely, this is quite a common one at higher, and therefore it was that grey area one, particularly the second one, of whether they would ask that or not at a National 5. The reason it's slightly uncommon is because discriminant wasn't part of credit or intermediate 2, but they've now brought it into the National 5. So that leaves us where the line drawn between National 5 and higher is slightly blurry. So again, prepare for this type of question at higher. So some examples. Example 1, what are the nature of the roots for the following quadratics? This should be a National 5 recap, so therefore it's a skill you're expected to be able to do with little to no difficulty. So A, if it's in standard form, just simply write down A, B, and C for the discriminant, which is b squared minus 4ac. Sub those numbers in, watch out for any negatives, squaring of negatives, things like that, multiplying two negatives together. Calculate your calculation. Remember, if you don't get the squaring right or you keep a negative where it shouldn't be, you can totally change the nature of the roots, and therefore in context-based questions at higher, totally change how the rest of the question plays out, and therefore may lead you down the wrong path where you don't complete the question and therefore can't gain full marks. So in this one, doing the sums, I get -8. What does a negative value for the discriminant show? Remembering from the recap and National 5, when b squared minus 4ac is less than 0, there are no real roots. Again, the real statement isn't really covered higher, but for those of you who go on to advanced higher, you'll soon learn why we make the statement real, because there is another domain of numbers. Second example, 4x squared minus 12x plus 9 equals 0. ABC again, 4 minus 12, 9. Sub the numbers in, watch out for the negative 12 being squared, that becomes positive 144, which leads to an answer of 0. When your discriminant is 0, you have equal real roots. Last example, x squared plus 7x minus 2. You can probably guess what's coming here. A, B, and C, 1, 7, and minus 2. Sub them in, and we end up with a discriminant of 57. Therefore, it's positive 57. So when b squared minus 4ac is greater than 0, we have two distinct real roots for that. Second example. Now, this is where we look at the second use for the discriminant, where we find a missing value based on information we're given about the equation. So have a go at these examples. For example 2a, when x squared plus kx plus 9 equals 0, when what value of k would give equal real roots? Well, they're telling you. When they tell you equal real roots, they're telling you the discriminant needs to equal 0. So that allows us to create an equation, and when we create an equation, we can solve it. In the previous examples, we were just finding a number. We weren't solving an equation. Here, we can solve an equation because we know a fact. We've been told a piece of information. So subbing the values in for A, B, and C leads us to having the equation k squared minus 36. Two options here. You could factorize it because it is equal to 0. It's got a squared term, and factorize by complete difference of two squares, sorry. Or you just solve this one since there's only one k term. So solving it, rearrange. If you choose to rearrange it, the key thing you need to remember, when you square root a number at higher, you must include both solutions. Square root 36 is both k equaling 6 and k equaling minus 6. So if the value of k was 6 or minus 6, the equation x squared plus kx plus 9 equals 0 would have, what was it, equal roots if you use the value of 6 or the value of minus 6. Second example, when 5x squared minus 2x plus k equals 0, when does it have two real and distinct roots? Well, when 5x squared minus 2x plus k, when a is 5, b is minus 2, and c is k. For two real roots, the discriminant must be greater than 0. So for two real roots, the discriminant must be greater than 0. So we sub in the values and we create an inequation. So we have to use the rules of inequations to solve. Watch out, key difference between an inequation and an equation is if you try to divide or multiply through by a negative, you must change the direction of the inequality sign. So in this case, I'm trying to divide through by minus 20. So watch out, when you multiply or divide by a negative, it changes the direction. So therefore, it will change the solution. K must be less than 1/5, not greater than. And for C, given that it's no real roots, that is telling us that our discriminant must be less than 0. So it's an inequation again. So 2 out of the 3 will always lead to an inequation when solving for k. Therefore, it will lead to a range of solutions, not just one or two. Solving 9 minus 8k less than 0 again. Watch out for the change in the direction, and k value of greater than 9/8 will lead to quadratic equation that will have no real roots. So it's quite powerful. It tells us a lot. And then, like I said, if these quadratics then have some context to them, this solution will allow us to make statements about what is and what isn't allowed, depending purely on the context. Third example is taken from a 2001 higher paper 1, question 2. Remember, that was the higher still, so that was before the changes to the new higher. So again, this was definitely a higher skill. Discriminant was purely found in the higher course, so therefore would be asked. I can't guarantee something like this would be asked in your higher, because it's that kind of grey area of what is and what isn't within the National 5 discriminant topic. So for what value of k does the equation x squared minus 5x plus k plus 6 equals 0 of equal roots? I picked this one because it's not as straightforward as the previous example too. So they're telling us that the discriminant is equal to 0 by those words of equal roots. So it's the trigger. A is 1, B is minus 5. But this is the important part. C is k and 6. Since it does involve x, the k and the 6 are considered the C coefficient. So be prepared to include both of that, because you've then got to take care algebraically when you sub it into the discriminant and rearrange to solve for x. When you do rearrange, you get a k value of 1/4. So when k is 1/4, this x squared minus 5x plus k plus 6 equals 0 will have equal roots. Fourth kind of area to look at now. Higher, you will have to deal with unusual forms for the quadratic. So it's not just limited to nice, straightforward x squared. You'll have to do quadratics that may also involve multiple unknowns. So it might be a p and a q. It could involve trig statements within. So basically what you're getting is a trigonometric quadratic, which is probably going to boggle a few people's minds. It might involve exponentials or logs. Again, these terms, exponentials and logs, will make more sense further down the course when we cover them. So an example of something that includes multiple unknowns, that could be qx squared plus px minus q. There's multiple unknowns there. So you could be asked to do something with a discriminant. You could be asked to do cos squared x minus 4 cos x plus 5 equals 0. So that is a quadratic trigonometric quadratic, because it's got trig terms, but it's got a squared, a non-squared term, and a coefficient. And so therefore the rules of quadratics can be applied. So example 4. Show that the equation qx squared plus px minus q equals 0 always has real roots. The q not equal to 0 is just purely a statement needed to be said that q cannot be 0, because if it was 0, you therefore don't have a quadratic, and therefore the rules of quadratics can't apply to it. So for there to be real roots, you've got to make sure there's got to be an x squared term. So they're telling you it always has real roots. So always, that means there's no possible values that you could pick for a q and p that would lead to a quadratic not having real roots. That in itself seems mind-boggling, but let's work through. The trigger has been real roots, so that should trigger you to use the discriminant. So our value for A is Q, our value for B is P, and our value for C is minus Q. Since it has real roots, that isn't that relevant at this point, because as it turns out, when we sub P squared minus 4 times Q times minus Q, we end up with an expression that's got P and Q. We're not going to be able to solve that. However, there are certain scenarios within maths where you're not able to solve or to prove by solving, but you instead have to reason out why something is definitely the case or why something isn't definitely the case. And we've been shown always has real roots, so we need to reason this out. Well, the key element to understand here is that it's p squared plus 4q squared. Now, since p and q are squared, the key feature of a square will always be a positive answer. So since the sum of two square terms will never be negative, b squared minus 4ac will always be greater than 0. Always greater than 0. Because there's no possible way of getting a negative out when you're squaring it, because the square will always rid you of the negative. So that's kind of a reasoning question where there's no solving involved because of the two unknowns, but you can still reason out a statement that will always be true. So therefore, since b squared minus 4ac can never be negative, therefore it will always be greater than 0. So therefore you will always have real roots, or it will always be greater than or equal to 0. So you will always have real roots. Second example, part B. Show that cos squared x minus 4 cos x plus 5 equals 0 has no real roots. Now, some of you might panic because there's trig involved with quadratics, but this is quite straightforward. They mention roots, so therefore this has potentially got something to do with quadratics. It's not quite a normal quadratic, it's a trigonometric one, but the rules of quadratics apply, as in we can apply the discriminant, so we take the coefficients. So it's so exact same way. A is 1. We don't take the cos x, that's part of the kind of x, so we don't need to take it into the as A. B is just simply minus 4 and C is 5. So we set up minus 4 squared minus 4 times 1 times 5. When we do that, we've proven it's minus 4. Since the discriminant for this this trigonometric quadratic is always minus 4, therefore there are no real roots. So this cos squared x minus 4 cos x plus 5 would have no real roots.